All right, this is the fifth section of this chapter, and we're talking about something called the normal distribution. This is a very common topic or something that comes up a lot in statistics and probability distributions. Back in section 3, we talked more specifically about discrete probability distributions. In this case, the normal distribution is a continuous probability distribution that we are going to talk about. So we're going to learn about something called the empirical rule that will help us analyze data that is normally distributed. And then we're going to learn to find something called z-values that lets us compare different normally distributed data. So the vocabulary you need to be on the lookout for here is normal distribution, empirical rule, z-value, and then what we call the standard normal distribution. So the normal distribution, so in this situation we have, this is a discrete distribution on this side, and here we have a continuous distribution on the right-hand side. So basically, as the sample size gets bigger and bigger, distributions tend to look more and more like this. They get more symmetrical, and they resemble this curve. This is called the normal distribution because of the law of large numbers. The larger and larger my sample size, the more symmetrical my distribution tends to be. So if I have a really big sample size, my distribution will tend to be normal or look like this curve. This curve at the right is called the normal distribution. It's continuous, it's symmetric. Sometimes it's called the bell curve, and it's a bell-shaped distribution of a random variable. And it's the most common continuous probability distribution, which is why we're going to be talking about it. So here are some characteristics of the normal distribution. It's continuous, bell-shaped, and it's symmetric around the mean. That means that right here in the middle, whatever this value is here is going to be the mean. The mean, median, and mode are all equal if I have a normal distribution, and they're located right here at the center. So this would also be the median and the mode right here. They would all be equal if it's normally distributed. The curve approaches but never actually touches the x-axis, so the x-axis is an asymptote. And the total area under the curve is 1 or 100%. So if I add together all the probabilities under this curve, I get 1 or 100%. So the area that's under that normal curve represents how much data is within a certain interval, or the probability that a random data value falls in that interval given a specific situation. So we use something called the empirical rule to figure out the area under a normal curve at specific intervals. Later we're going to see what happens if our intervals aren't as specific as they're going to be here. But the empirical rule says if I have a normal distribution with a mean of mu and a standard deviation of omega, again mu or my mean is here in the middle. And then this plus or minus omega, remember that omega is a standard deviation. So if I take my mean and I add one standard deviation, in this section there will be 34% of my data. If I subtract one standard deviation, I have 34% of my data here. So that means that 68% of my data is within one standard deviation below or above the mean. And you can see the other numbers after that. 13.5% is between 1 and 2 standard deviations above the mean. So this is 1 standard deviation, this is 2. Oh, and 13.5% is 1 or 2, between 1 and 2 standard deviations below the mean. So altogether, 95% of my data is going to fall within 2 standard deviations below or above the mean, and so on. So let's take a look at what this would look like in an example. We have a normal distribution. My mean, which is mu, is 45.1, and my standard deviation, omega, is 9.6. So I want to find the values that represent the middle 99.7% of the distribution. If we look back here, 99.7% goes from the mean minus 3 standard deviations to the mean plus 3 standard deviations. So we're going to take a look at that, and we can do it by kind of drawing a picture, or we can just do it mathematically. So the middle 99.7% of data goes from the mean minus 3 standard deviations to the mean plus. So if I take my mean and I subtract 3 standard deviations, I get 16.3. If I take my mean, mu, and I add 3 standard deviations, I get 73.9. So that means that 99.7% of the data is between 16.3 and 73.9 in my normal distribution. Another way to do this would be to make a graph or a picture. So my mean is here in the middle, 45.1. Then to get from my mean to my next value, I add 1 standard deviation of 9.6. To get to my next value, I add 9.6. And to get to my next value, I add 9.6. So there I added 3 standard deviations to the right, so I got to 73.9. And then I would subtract 9.6 to go 1 standard deviation below, subtract 9.6 to go a second one, and subtract 9.6 to go a third one, and I get to 16.4. They had 16.3. I'll check that, but it might be 16.4 instead of 16.3. But I can draw my picture and do the math and get those values in the same way, or I can just use the formula. All right, part B says what percent of the data will be greater than 54.7. So this 54.7 is a value, not a percent. Again, I have my mean of 45.1. So if I look back at the curve I drew here, which is not a very beautiful curve, but anyway, 45.1 is my mean. 54.7 is 1 standard deviation above the mean. So if I'm asking what percent of the data will be greater than that, I'm asking what percent of the data will be more than 1 standard deviation above the mean. So since that's 1 omega, or 1 standard deviation more than the mean, I know that 68% fall between 1 standard deviation below and above. So everything else covers 32% of the distribution. I only want the upper tail. So 16% of the data will be greater. I'm going to go back and show you this on the picture because I think it will be easier. I'm going to go back to the empirical rule. So what they're saying is my 54.7 is right here. So if I have 54.7, they're asking how much of it my data is greater than that. Well, it's going to be this 13.5% and this 2.35%, and then everything else that's beyond that, right? So notice that only 99.7% is included within 3 standard deviations of the mean. So I know that there's a full 100%. So if only 99.7% is represented here, that means there's 0.3% left over. That means 0.15% has to be way out here where I can't see, and 0.15% has to be down here. So what percent is greater than 54.7? 13.5 plus 2.35 plus 0.15, which is 16%. All right, try this one. All right, your answer here should be B, 2.5%. Okay, so in this situation, I decided to draw the curve. So here in the middle, I have my mu, my mean, 38.3. 1 standard deviation below takes me to 32.4, and another standard deviation below takes me to 26.5, which is what they're asking about. And they want to know what percent of the data is less than that. Well, I know that 50% of my data has to be above the mean. I know there's 34% between the mean and 1 standard deviation below, and 13.5% between 1 and 2 standard deviations. So basically I have 100% minus 50% minus 34% minus 13.5%, and that leaves me with 2.5%, which you could get by looking again at your empirical rule. That'd be 2.35%. And then in the last example, we talked about how out here at the tail, there's another 0.15%, and together that would make 2.5%. All right, take a look at this example. It says students counted the number of candies in 100 small packages and found that the number of candies per package was normally distributed. The mean was 23, and the standard deviation is 1. How many packages would be between 22 and 24 candies? Well, if I think again about my normal curve, I know that my mean here is 23, right? So 23 in the middle. 22 is 1 standard deviation below, and 24 is 1 standard deviation above. How much data is between 22 and 24? Looking at your empirical rule, it is 68%. And notice it says how many packages, not what percent, right? So since there are 100 packages, 68% of 100 is actually 68 packages. But make sure you pay attention to whether or not they're asking for a percent or an amount. All right, please try this one. Notice they're asking for the probability, which will be the percentage, not the amount. All right, your answer here should be D. And this is an example of how you could have figured that out. Between 23 and 32 students, 23 is 1 standard deviation below, so I know there's 34% between the mean and that number. Then from 29 is 1 standard deviation below, that takes another 34%. And then to get to 32, I have to go another standard deviation, and the percentage there is 13.5%. So notice they're not asking the number of students, they're asking the probability. So if I select a class at random, the probability of it having between 23 and 32 students is 81.5%. All right, we're going to go through this last part really quickly. We're going to talk about something called the standard normal distribution. The empirical rule is only useful if we know specific values that are exactly 1, 2, 3 standard deviations above or below the mean. But once we do something called standardizing the data, I can evaluate any data value, even if it's like 1.25 standard deviations below the mean. I standardize data by converting them to something called a z-value or a z-score. You'll see both of those. A z-value represents how many standard deviations any value is away from the mean. And I can figure out, with a z-value, I can figure out where a data value is in my set. So here's the formula for the z-value. X is a data value in my set. It has to be normally distributed for this to work. So the z-score is the data value minus the mean divided by the standard deviation. So first we're just going to kind of learn to manipulate the formula a little bit. Here they're asking me to find the standard deviation if I know the data value, the mean, and if I know my z-value. So in this case, my z-value is 0.63, meaning that 28.3, my x value, is 0.63 standard deviations away from the mean. So I just plug into my formula. All this is solving for a variable, and I multiply both sides by omega, divide by 0.63, and I end up with omega being about 5.87. So that would be my standard deviation. Remember, omega is the standard deviation. And since z is 0.63, it means that x is 0.63, again, standard deviations away from the mean. So you guys try this one, find mu. All right, in this case, mu should be A. And this is how you should have set it up, and then you should have solved for mu to get 26.082. Okay, so the question might be in your mind, why are z-values helpful? If I have normally distributed data, really any combination of mean and standard deviation can be possible. So that can make it hard to compare two distributions if their means are different and their standard deviations are different. But if we convert them to z-values, we can compare with the standard normal distribution. So we standardize our data with z-values, and then we use the standard normal distribution. So again, the percentages are the same, you'll notice, so it's not that different. It's symmetric. The mean is 0 when I convert to z-scores, when I standardize my data, and my standard deviation is 1. So 0 is the mean, and then 1 means it's 1 standard deviation above, -1 means it's 1 standard deviation below. But notice all the other percentages are the same. Don't forget about that 0.15% out to the left and the right. So the standard normal distribution lets us assign areas to intervals created by z-values that don't just have to be at -3, -2, and -1. They can be anywhere on this x-axis. And I can find the probability just like I did before using the percents. So let's take a look at this example. The cholesterol level for adult males is normally distributed. It has a mean of 158.3 and a standard deviation of 6.6. And they're asking us to find the probability that a data value would have a cholesterol level greater than 150. All right, so I need to find my z-value first before I do anything else. I'm going to find my z-value for 150. So I use my formula. And when I simplify, I get a z-value of -1.26. So that means that my cholesterol level 150 is -1.26 standard deviations away from the mean. So it's 1.26 standard deviations below the mean. And then we're going to use a graphing calculator to get the area under the curve. I'm going to show you that real quick. In your calculator screen, you go to Statistics, Distributions, and Normal CDF. My lower bound is my z value, and I'm going to the right of that. My upper bound we're going to say is 4 standard deviations.